Let's have a closer look now at what happens when we add together waves of different frequencies. In this case, I've got a blue sine wave, and I'm going to add to that a red sine wave. And we see at some points they are in phase and they'll add up and give constructive interference. At other points they're out of phase, and this will give us destructive interference. So if we add them up, we get something that looks like this. Some places it's big, twice the size of the original waves. In other places it cancels out and we get something close to zero. Now this phenomenon is known as a beat, and the difference between the two frequencies that gives us this modulated signal is called a beat note. So the frequency of this modulated signal is called the beat note. In this example we have 10 blue wavelengths for every 11 red wavelengths. What that means is that every 10th blue wavelength the interference condition repeats and you'll get constructive interference. So if we counted along 10 blue wavelengths here, we start off with constructive, and over here we get constructive again. And in between you have destructive interference. Now, a neat physical example of beats that you may have seen are those you see at the beach. If you're sitting out waiting for a wave to come, if you're surfing, sometimes you find that the surf is pancake flat, and then a few minutes later you're being rolled by some enormous waves that you didn't see coming. The reason for that is beating, interference between waves of different frequencies. If you add up all the different waves in the ocean, they have lots of different wavelengths, lots of different frequencies. Sometimes they add up constructively, like these times with the red arrows, and sometimes they add up destructively, so you get periods of very small wave amplitude and periods of very large wave amplitude depending on how these different waves of different wavelengths and frequencies add up. Now the ocean is much more complicated than this example with two simple sine waves, and so the beat is not regular. In this particular example, the average time between constructive interference, so the sets, is 8.8 minutes, but that's just for this example. It depends on where the different storms are and what's generating the waves as to how frequent the sets are or how big the contrast between the constructive and destructive interference will be. Nevertheless, if you've ever wondered where sets come from when you're surfing, that's beating between waves of different frequencies. Here's an example of an acoustic beat note. We're going to play two different frequencies on top of each other, one at 1000 Hz and the other at 1002 Hz. We turned on, we hear this rather irritating sound. The frequency you hear is 1001 Hz, so it's the average of these two frequencies, but it's being modulated, it's turning on and off at a rate of 2 Hz, which is the difference between these two frequencies. If I change the beat frequency to say 1 Hz, now it's turning on and off at a frequency of 1 Hz. And again, the carrier underneath is the average of these two frequencies, which is 1000.5 Hz in this case. We've looked at beats qualitatively, now let's get quantitative. We're going to consider some function of time, which is sum of two sine waves, frequencies omega-1 and omega-2, with some phase shift if we wish. We're going to rewrite this sum of sine waves as a product of a cosine and a sine, and we can do that using this trigonomic identity here that turns this sum of sine a plus b plus sine of a minus b into this product. And so in order to use this trigonomic identity, what we need to do is solve for a plus b being equal to omega-1 times t, so it would be this term here, and a minus b being equal to omega-2 times t plus phi, so it would be this term here. It's a pair of simultaneous equations for a and b, so we solve for a and b. Here's a, and here's b. We can substitute it into this expression here. So now our function of time, which used to be the sum of sine waves, is now written as a product of a cos and a sine. If we look inside these arguments here, we see that the cosine is the difference of the frequencies divided by 2. And if these frequencies are close together, this will be a small frequency. For this function here, we have the sum of the frequencies divided by 2, so it's the average of the two frequencies. So if omega-1 and omega-2 are large, then this will be a big frequency. So for example, if we have omega-1 is 1002 Hz, and omega-2 is 1000 Hz, then the function of time would be cos 2 pi t, so this is a frequency of 1 Hz, and sine 2 pi 1001 times t, so it's a frequency of 1001 Hz. So this is a fast frequency and a slow frequency. Now these two frequencies have names. The fast one is called the carrier frequency, so that's the average of the two frequencies, and the slow one is called the envelope frequency. You might hear this sort of terminology when you talk about radio transmissions. The envelope frequency, by the way, is also sometimes called the modulation frequency. In AM radio transmission, the carrier frequency is the frequency you tune your radio dial to. So for example, with AM amplitude modulation radio transmissions, if you want to listen to Radio National in Canberra, you would tune your radio to a frequency of 846 kilohertz, and that is the carrier frequency. The information that's carried in the radio signal is the envelope, or the modulation frequency, and that's the part which multiplies the carrier. So this would contain the audio signal. In this case, you'd be listening to something pretty boring because it's just a cosine wave. But if you, instead of multiplying this carrier by a simple cosine wave, you multiply it by the sound of someone speaking, then when you demodulate this signal, and your radio demodulates it, then you get this audio signal back again. So here I've plotted the beating again on a graph. So this brown wave, this fast one here, the frequency of that is the carrier frequency, and the slow blue is the envelope. But if we look at this signal, what we see is that the period of the beat here seems to be twice the period of the envelope, because when the envelope multiplies the carrier, you get some beating when the envelope's positive, and you see some beating when the envelope is negative, and everything cancels out when the envelope goes through 0. So now the envelope frequency here is omega 1 minus omega 2 divided by 2, but the period of the beating that you hear is twice that, because every time this signal recurs, you'll hear something. You hear nothing in the middle here, but you hear something, whether this beat is multiplied by the positive part of the envelope or the negative part. So when you hear the beat, the frequency here is the difference in the two frequencies, not the difference divided by 2, but what you hear is just the difference in frequencies. So the frequency of the audio beat as you perceive it, in this case, would be twice the envelope frequency.